Okay, so now we are good to go. Yes. Okay, so today we are going to be going over 9B, section 9B, which is on linear modeling. And linear modeling, what that means is really that there's a uh, constant change over constant change, actually. So an example of I'm going to start with an example. An example is going to be something like a savings account. So if we look at this, let's say we put $10 in a savings account each month. This is a really good example of linear modeling because there's constant change. We're putting $10 in a savings account each month. Now, for our example, the savings account is not going to draw interest. Okay, it's just putting it in a jar or something of that nature. So let's look at a graph. We're going to actually graph it. So the x-axis, so remember that was the independent variable. We're going to have months. And then the y-axis, which is the dependent variable, we're going to have just the amount of money in there. So we're going to start at 0, and then the first month, second month, third month, and fourth month. Now, I'm going to do this in 5s, the notches here. Well, actually, let's just do 10s. So 1, 2, 3, 4. So this will be 10, 20, 30, 40. Now I'm going to do little notches in between just to show the 5s. Okay, so let's graph this example. So at the very beginning, we have $0, right? So we're right here. And then after the first month, we're going to put $10 in. Boom, we're right there. The second month, we're at $20. The third month, we're at $30, right? The fourth month, we're at $40. And what you notice, it creates a straight line because it's a constant change each month. Each month, we're putting in $10, so therefore we're going up $10 a month, creating a nice linear, that's where this section comes from. This is a linear model. Linear because it's a straight line. Okay, linear because it's a straight line. And with that straight line, we can actually find its rate of change, which is also known as a slope. So you're going to hear the word rate of change and just realize it's slope. So if you've never seen this before, that's fine. I'm going to go over it, but we can find the slope. And what this slope is, actually, your book defines it as, it's on the bottom of page 527. It's the change. Now you can use a delta symbol, a triangle for change in the dependent variable over the change in the independent variable. So if we look at these, now we're going to look week to week here. So I'm going to kind of draw, let me use another color here. I'm going to get some, yeah. I'm going to just choose this change right here. Okay, so from week 2 to week 3, well, think about this. The change in the, now I'm going to write these down because I love forgetting. This is the independent variable, and this is the dependent variable. Okay, so the change in the independent variable was 1 week, right? 1 week to the right. So from 2 to 3, we went from 1 week. The change in the dependent variable is we gained $10. That was the change. So from week 2 to week 3, we kind of ran 1 week over. We went 1 week over and we went $10 up. So that's actually the rate of change. So the rate of change comes from this. So the change in the dependent variable, so the dependent's the y. So the change in the dependent variable was $10. And the change in the independent variable was 1 week. Okay, so we can write this as $10 per 1 week. Now, typically we write it as $10 per week is fine. You can leave it in this form, but what's nice is it has units to it. So if you wanted to write it as $10 per week, there's nothing wrong in that, but that's actually our slope. That's our slope. We went over 1 week, up $10, right? Over 1 week and then up $10, and boom, we have the rate of change for our equation. Now we kind of know this, right? Because we said, look, there's $10 in the savings account, or we add add $10 in the savings account each month. That's what's going to happen. Okay. So let's say you get a different job and you can put more money in your savings account. So you decide to put $20 each week in your savings account. And let's graph this. So we're going to do $20 each week. So the first week you're going to have $20. The second week you're going to have 40. We're already kind of off the chart here, right? So this is a different savings pattern. So this line right here represents a different savings pattern of $20 per week. And we're going to do the same thing though. We're going to find the rate of change for this guy. So it's still going to be 10, but I want to show you graphically what's going on. So let's say from week 1 to week 2 now. So we go over 1, still over 1 week, but then we're going up $20. Okay, so the rate of change for this one would be $20 per 1 week. So it's going to be $20 per week. Okay, and notice this line is much steeper. So when your rate of change increases, so this went from 10 to 20, when your rate of change increases, the line gets much steeper. Whenever we have a less steep line, let's say we can only save $10 a week, or $5 a week. So if we did $5 a week, it would look something like this. Let's say there's the first week you'd have $5, the second week you'd have 10, the third week you'd have 15, and the fourth week you'd have 20, right? So it would look something like this. So the line is the least steep for $5 a week, okay? And look, you can find a slope or a rate of change over multiple x-axes if you want, or x units if you want. So let's say we went from 2 to 4. So I want to go from here to here. So 2 weeks over. So in 2 weeks, I go up, for this example, I would go up $10 for 2 weeks, right? Because I was saving $5 each week. So it went from $10 to $20. So my rate of change would be 10 over 2, which turns out to be $5 per week. But notice the $5 per week slope, that rate of change is the lowest. It's the least steep, okay? With linear equations, the more change per dependent variable, the steeper the slope is going to be, okay? Your book kind of goes over that on 527 with a different example with rain. But, and if you want to look at it, if this one's not quite making that much sense, you can look at that one. It's another example of this topic, okay? Now let's make sure I'm going to read through this to make sure I haven't missed anything. At the bottom of page 527, it says a linear function has a constant rate of change with a straight line graph. So like each one of these has a constant rate of change, right? Like if we stick to this black one, the rate of change is $10 per week. The greater the rate of change, the steeper the slope. Yeah, we can calculate the rate of change by this equation. So good, we've got that covered. Okay. And then it goes into drawing linear models. You can look at that. That's not a big deal. I'm going to actually look at the second example there, which is a price demand function, which is pretty neat in the real world. For a real world example, this is a pretty cool one. Okay, price demand function. So a price demand function is developed whenever, let's say you've got a product and you're not sure what to sell it at. And you can kind of test the market by doing this. So you can do price demand functions by testing the market on what you should sell the product at. And your book, I'm going to use the book's example, but you don't have to. You can make one up if you want. This is on the bottom of page 528, example 2. It says a small store sells fresh pineapples. Based on data for pineapple prices between $2 and $5, based on data for pineapple prices between $2 and $5, the store owner creates a model in which a linear function is used to describe how the demand or the number of pineapples sold per day varies with the price. So for example, so the first point they give is for this first day, they sell pineapples for $2. $2 pineapples. And they sell 80 pineapples. Should say $2 price. That's a better way to, let's write it like that. $2, when they set the price at $2, they sell 80 pineapples. So, I mean, if we think about this, if you sell 80 pineapples for $2, your revenue, now there's cost involved, right? But your revenue is going to be $160. They made $160 off these 80 pineapples. Well, the next example they give, okay, well, hold on. $2 pineapple, yeah. They've got to give me another example. Why does the rate change? Just wait, hold on. Do they not tell us another amount? They've got to tell us the $5 for $5.50. Oh, they goofed up on this example. So it's, hold on, let me read through it. A small store sells price, for example, 80 pounds. What is the average? Well, yeah, the rate of change. Okay, they left out on that example. They left out the other coordinate. So it turns out another day they sell $5 pineapples as the price. Now, of course, think about this. If you up the price from $2 to $5, you're going to sell less pineapples, right? And it turns out they only sell 50 pineapples. Now think about this. It sounds like a good deal, right? For the company, like, oh yeah, I'm going to just sell more and I'll make more. But you sell them for $5, you sell less. 5 times 50, oh hey, that's $250, right? We actually made more by upping the price here, right? $2 you sold 80, that's $160. $5 you sold 50, that's $250. It was worth, even though we sold less pineapples, it was worth increasing the price to us, okay? But what's neat about this is it creates two coordinates for a graph, okay? So let's look at this. So the first coordinate, so that means we're going to make the first coordinate 280 and the second coordinate 550. So by doing that, our x value is price, and then our y value is the amount sold. Amount of pineapples sold, okay? And let's just kind of graph this. Your book does this too. I'm not doing anything crazy, but your book does this as well. So let's say 2, we've got 82, and then 3, 4, 5, 60. So if we go up to 80, let's go up to like 100 here. So if here's 100, this would be 50. So 1, 2, 3, 4, 1, 2, 3, 4. Okay, so this is going to be hundreds of dollars here, guys. So this would be like 10, 20, 30, 40. We'll put the 50 here, 60, 70, 80, 90, 100. Okay, so this is the price, right? The price of the pineapple. And this is, oh, I lied. This is the amount sold. And this is the price. Okay, and we know two of these numbers here. So hold on, let's do 1, 2, 3, 4, 5, 6. I guess we'll keep going if we want. But the two prices we know are 280. So we know at $2 for the price, we sell 80 of these things, right? And at $5, we sell 50. So this equation, if we kind of graph this line out, this equation is going to be linear, but it's going to have a negative slope here, right? Which kind of makes sense. I mean, the reason it would have a negative slope is because as our price increases, we expect to sell less pineapples, right? So therefore, we're going to get this negative slope. They have an inverse relationship. We talked about that in the correlation causation section, right? As this price increases, we're actually going to be decreasing the amount we're selling. Now let's look at these two prices, and I'm going to make this stair step to make the rate of change, okay? Because it's not nice like the other one. It's not nice like a nice, like for 1 over, you go up 10. No, it's not like that. So let's look at this. So we go from 2 to 5. So we changed $1 to $3. We went $3 to the right, and then really we're going down here. So now we were at 80, and then we go to 50. So that's $30 down. I'm sorry, 30 pineapples. 30 pineapples down, okay? So if we want to make a rate of change here, now remember, it's the change, it's the, oh gosh, I don't want to do these backwards. Yeah, it's the dependent over the independent. So it's the change in the dependent. Now look, if this is going down to go to the right, this is going to be negative. It dropped from 80 to 50. So it's down 30. So it's negative 30 pineapples over, now we went to the right $3. Okay. Yeah, $3 in price. So what does this mean? So we get negative 10 pineapples per dollar, right? Per $1, if you want to write it like that. So what does this tell us? And hold on, let's look at this. And it's what your book got. It's in the middle of page 529. And it says, well, what this means is the rate of change of the demand function is negative 10 pineapples per dollar. So for every dollar that the price increases, we're going to sell 10 less pineapples. Okay, I'm going to write that down. For every dollar increase in price, we will see, and I should say we should see, right? This is not perfect. If you try this in the real world, you're not going to get perfect things, right? But we will see, or we should see, 10 less pineapples sold. Okay, that's what this is telling us, which is kind of cool. Excuse me, kind of neat. So for every dollar increase, we should see 10 less pineapples sold. And then the next section, okay, hold on a second. So then let's just read what they say. They keep going. This model seems reasonable within the domain for which the pineapple gathered data, between $2 and $5. Outside this domain, the model's prediction probably are not valid. For example, the model predicts that the store should sell 1 pineapple per day at a price of $9.90, but that could never sell, but could never sell a pineapple at a price of $10. Yeah, right. So I mean, think about this. If we kept increasing the price, like if we know we go down $3 and over 30, so if we go down another $3, I'm sorry, if we increase the price another $3, so this was at 5, 6, 7, 8, right? Down, we're going to go down 30 and then over 8. So this point right here would be, $8 for the price. But then remember, we started at 50, now we go down, so this would be 20 pineapples sold. So if we set the price of pineapples at $8, they're saying we should expect to sell only 20 pineapples, which is kind of crazy. 8 times 20 is $160. That's the same as selling $2 pineapples for 80. Okay. But the store owner is like, no, there's no way we could sell them for $8. Actually, if you read at the beginning of this example, he's only looking at selling the pineapples between 2 and 5 because people just don't buy pineapples after $5. So this isn't really included in the domain, any of these values, because of his knowledge, right, of the market. So it just wouldn't go up this high. And then same, it wouldn't go the other way either. It doesn't, I mean, if you sell 50-cent pineapples, you're going to sell them all day, every day, but you're not going to make your money back. So he's not going to sell for less than $2, probably because of the cost involved in putting the pineapple on the shelf, right? That's why in the statement, he said it's got to be, let's say he, could be she, between $2 and $5. The shop owner said, look, these pineapples have to be between $2 and $5 for the store. Okay. Kind of neat stuff. And really, I mean, think about this. This is how a lot of guest checking kind of in the market on how this happens. And this can relate to a maximization function too. We won't get to that, but it's pretty neat how it can go into how to maximize your revenue. Okay. I mean, actually, look, if you just chose these two numbers, look, we should be selling $5 pineapples because we have $50, right? The revenue is 5 times 50, $250. This is 2 times 8, it's $160. We should be selling. If I was a consultant for the shop owner, I'd be saying, put your pineapples at $5. Yeah, you're selling less. But hey, that means there's less pineapples on the shelf. You got more room for something else to sell. So you got more room on the shelf for something to sell. You only have to sell $50 or 50 pineapples a day, and you're making more than if you made them for $2. So don't worry that you're selling less. You're actually making more in revenue. Okay. That's why I like that example. Okay. So the rate, now let's look at the top of page 530. It says the rate of change rule. It says the rate of change rule allows us to calculate the change in the dependent variable from the change in the independent variables. And it looks like this. The change in the dependent just equals the rate of change times the change in the dependent or independent. Now, this is just coming from the slope formula. They're just multiplying this over the change in the dependent over. Does your book? Yeah, your book does an example in the last. Oh, they went off the other one. Look, we can. I don't know if we can use. We'll use this this example with the pineapples. Okay. If I wanted, let's see here. So we want the dependent, which would be. Hold on a second. Yeah, the dependent. Yeah. So if I want the change in the amount of pineapples sold, okay. Okay. I want the change in the amount of pineapples sold when the change in, well, okay, suppose we want to know how much the rate of change is in a 4 hour period. So is the rate of change for this function is 1 inch per hour? Yeah. When this doesn't work well for our pineapple example. I'm going to mark that out. It just doesn't work that well for this example. And let's look at their example. We'll do it. It just doesn't work well for the pineapple one. It says, consider again the rain depth. This is on the bottom of page 529. Consider again the rain depth function in figure 9.8. Suppose we want to know how much the rain depth changes in a 4 hour period. So how much does rain depth change in a 4 hour period? Because, okay, now, so let's go back real fast and look at their example. So 9.8, figure 9.8. Okay, it's on page 526. And they found out that their slope is 1 inch per hour. Okay, 1 inch per hour. So that means the depth is the dependent variable, and then the time is the independent variable. Okay, so if we want to know how much does rain depth change in a 4 hour period, so what they're really wanting to know is from the example before, the change in the dependent, because that's the depth is the dependent. So the change in the depth over a 4 hour period is just going to be the rate of change, which is 1 inch per hour, times the change in the independent variable. Well, in the question, it says during a 4 hour period, and the independent variable is time. So the change in that variable is 4 hours. 4 hours. And what happens is your hours cancel. So you get 1 times 4 and you get 4 inches. Okay. So during that time, it changes, it raises 4 inches. I wouldn't say that that's that big of a deal. The bigger concept's really in the next part, which is the equation for linear functions. Okay. The equation for linear function, which starts on page 530. So let's just read through this for a minute. I'll tell you there's pros and cons to how they do their example for linear function. You've all heard the equation y equals mx plus b. That's a linear function. The issue is y equals mx plus b is just not written correctly. Let's look at another example about saving money. Okay, actually, let's do one with spending money instead of saving money. Let's say you put, let's say $100 in a savings account, So you've got $100 in savings. And each month, a fee comes out, is taken out of that account for $5. Okay. And let's say if we didn't add any more money to our savings, let's model this example. So if we go up to $100, so let's say $100 is here, right? Since we start with $100, our equation actually is going to start right there on this dependent axis, right? This is the dependent, this is the independent, and this is the amount in the dollar amount, and this is again months. So we know after the first month it's going to go down $5. So let's try to make this a little. Oops, I think I made these in 25 unit. 1, 2, 3, 4, 5, 6. Oh gosh. Oh no, I really messed up the axes. Let's say these are just $5. So let's say this isn't 0. So this goes down to 95, 90, 85. And then it actually doesn't, it's not written beautifully. But after the first month, we know we're going to be at $95, right? After the second month, we're going to be at $90. The third month, we're going to be at $85, right? And the fourth month, we're going to be at $80. So it's going to have this nice, not nice, I guess, but it is going to be a linear function. But it's negative, right? Because our slope, if we wanted to find our rate of change, remember it's the change in the dependent. Well, this change in the dependent is -5, right? It's going down $5 for each 1 month. So it's going to be -$5 per month. Okay. So that's going to be our rate of change, right? That's going to be our rate of change. So it turns out if you wanted to make an equation for this, if you wanted to create the equation, your book starts with, it's on the bottom of page 531 in green, and it's the general form. General form of a linear function. Yeah. It's going to start with a dependent variable. And it's going to equal your initial value. So your initial dependent variable. And then plus the rate of change. Times the independent variable. I ran out of room here. Okay. So it's your dependent variable, and it's going to equal your initial value plus your rate of change times whatever the independent variable is. Okay. So for our example, let's look at this for a minute. For our example, our dependent variable, we're just going to use the y value because it's our y-axis. So we're going to use y. Y equals your initial value. Well, it's the initial dependent value. And remember, we started with $100 in this savings account. So our initial value is going to be $100. Okay. Plus, now our rate of change, which we had to find, it went down 5 over 1, right? Down $5 over 1. So therefore, our initial value is going to be, our rate of change is going to be -5. I'm not going to use units in here now at this point, okay? And then we're going to multiply that by our independent variable. Well, our independent variable is right here. It's the x-axis, okay? That's our independent variable. So I'm going to use an x. So the general linear form, I'm going to clean this up a little bit, is going to be y equals 100. Now for this example, because the rate of change is negative, I'm not going to put plus -5 times x. I'm just going to say -5x. This would be our equation for our linear function. And think about this, like if we chose a month that we know in month 3, we're going to be at $85. Let's plug month 3 into this independent variable. If I plug 3 in, I'd have, okay, you know what? I'm going to do it up here. So I've got y equals 100 minus 5 times x, right? y equals 100 minus 5 times, well, what's happening in the third month? 100 minus 15, yep, y equals 85. That checks out, right? Because at the third month, our y value is going to be $85. That's for a specific month that we plug in. Pretty neat, okay? So this is the linear function. This is how to create a general form of a linear function. Now, for whatever reason, someone decided to not write it like that anymore. And they decided to write the rate of change first. And by doing that, you get the slope-intercept form. Yeah, the slope-intercept form. I'm going to write it like that. And all the slope-intercept form does is write the rate of change before the initial value. So for our example, 100 minus 5x, the slope-intercept form is going to be negative 5x plus 100. All you do is put the rate of change times the independent variable first, and then you put the initial value second. And a lot of students have seen this before, right? It's y equals mx plus b. M is your slope, negative 5 is our slope, it's our rate of change, and b is our y-intercept. Yeah, well, b is the y-intercept. It's where we initially start on the y-axis, okay? So y equals mx plus b is what you've probably heard before. Okay. Your book goes over some good examples about like alcohol metabolism. There's another price from the demand equation. Hold on, what is it going into? We can do some of these. Equation of a lot, okay. Let's do the alcohol metabolism. This is on page 532. It's example 5. And it says, alcohol is metabolized by the body through enzymes in the liver in such a way that the blood alcohol content decreases linearly. A study by the National Institute on Alcohol Abuse and Alcoholism showed for a group of fasting males who consumed 4 drinks rapidly, the blood alcohol content rose to a maximum of 0.08 grams per 100 milliliters. About an hour after the drinks were consumed, that's all one sentence. 3 hours later, the blood alcohol content had decreased to 0.04 grams per 100 milliliter. Find a linear model that describes the elimination of blood alcohol after the peak blood alcohol content is reached. According to the model, what is the blood alcohol content after 5 hours? So I'm a drawer. I like drawing, so I'm going to draw this. So we've got time, which I think they did in hours, right? So we've got hours here. We've got blood alcohol content here, okay? Put up the red. It's blood. And let's draw what we've got going on. So it says it peaks. They want to start where it peaks at 0.08. Okay, so you've got 0.08 blood alcohol content right there, and that's where we're going to start. And what happens is they found is once it peaks, it dies off linearly, okay? And then after 3 hours? It's at 0.04. So 1, 2, 3. After 3 hours, we're at 0.04, which we know is half, right? So, which, of course, means after 6 hours, we would be at 0 because we've got this linear change, right? We go down 4 blood alcohol content, and then we go down another 4. Whatever unit that is, okay? We wouldn't go negative here. You can't have negative blood alcohol content, right? But it looks like this. So once you hit your maximum, it just dies off linearly. It looks like you have to fast. I guess if you eat, it probably changes that blood alcohol content as well. So it goes down linearly. So let's actually create this equation. We know the initial value, so I'm going to start here. I'm going to say y equals, my initial value is going to be 0.08. Right? Plus, now remember it's the change. Hold on, let's find it here. Oh yeah, here we go. It's the rate of change. So my rate of change, look, this goes down 0.04 in your blood alcohol content for every 3 hours, right? So I'm going to write that as a fraction. I'm going to say Negative 0.04 is the change in the y value over the change in the x. 3. Okay, I'm not going to put units in here. I'm just going to leave it as numbers. So minus 0.04 over 3 times my x value, my hours. Okay, now I'm going to clean this up. Let's see in our calculator here if that actually makes a nice linear or a nice number. I bet it does. So 0.04 divided by 3. Oh, so math, frac, 1/75th. So, well, they rounded with a decimal. So y equals 0.08. Now it's a negative over a positive, so I'm going to write as negative 0.0133. They round it. X. So that's my equation to this linear function, to this linear model. Okay, kind of neat. So that's my equation to linear model. Now, the next question, there's 2 questions involved. It says, according to the model, what is the blood alcohol content 5 hours after peak? So what's the blood alcohol content after 5 hours? So what they're giving us is actually an X value, right? We know at 5 hours visually, it's somewhere down here. I'm not exactly sure where it lines up on my y-axis. So I'm going to use the equation. So if x equals 5, I want to know what's the y value. That's what it's asking. So I'm going to say y equals 0.08 minus 0.0133 times 5. And I'm just going to pop that in my calculator. So 0.08 minus 0.0133 times 5. And I get 0.0135. So that would be my blood alcohol content after 5 hours. If I peaked at 0.08 and I didn't eat anything, it just dies off linearly. And so after 5 hours, I'll be at 0.0135. Pretty neat. Okay. Okay, the last question, which I think really is kind of like the one we did before, is what if we're only given 2 data points? How can we find a linear equation if we're given 2 data points? So I'm going to just steal their example again. And it's pretty straightforward, actually. The goal now is to find the initial dependent variable. So yeah, okay, so I'll go through this with you, and it's not too bad. And I will use their example just to follow along with the book. It's on page 535. It says about crude oil use since 1850. It says until about 1850, humans used so little crude oil that we can call the amount 0, at least in comparison to the amount used since that time. By 1960, humans had used a total of 600 billion cubic meters of oil. Ooh, excuse me. Create a linear model that describes world oil use since 1850. Well, that seems pretty straightforward. Hold on. Okay, so we've got these 2 coordinates. Let's make our x value is years, and then y value is, let's do crude oil. I think they do it in billions. Oil in billions, okay? So in 1850, we were using no oil, right? I mean, they said it was so little, you might as well say it's 0. In 1960, though, we were up to 600 billion cubic meters used. Okay, and it's used by 600 by 1960. So it's not that in 1960 we used 600, it's that through this entire time we had grown to 600. Okay, so let's find the rate of change. Let's find the slope. Now what's nice, look, I'm not going to draw this. We know the slope is the change in the dependent variable over the change in the independent, right? So let's look at the dependent. Now the dependent value is the y value. We've gone from 0 to 600. So we've increased 600 billion crude oil barrels or whatever it was, okay? And then in time, though, the independent variable, we've gone from 1850 to 1960. That's what, 110 years. We've increased 110 years. So this would be our slope. 600 divided by 110. I bet it is a nice number. Yeah, it's, well, not really, but it's 5.45 would be our slope. Okay, that's going to be our slope. Now, let's go back to that equation for the linear model. And your book uses the slope-intercept form. So the slope-intercept form would be y equals our slope, 5.5x. Now, look, we don't know our initial, our b value. We don't know the initial y value, or not y value. Yeah, we don't know the initial y value when x is 0, so when time is 0, which is kind of goofy here. It's kind of theoretical. And what you're going to have to do is you're going to have to find this b value. And the way you do that is you use one of the two coordinates, okay? I'm going to use this first coordinate, and what you do is you plug it in to the x and the y values, okay? And it'll leave you with a b value. So let's look at an example here. So if we plug these two coordinates in, it would be 0 equals 5.4 times 1850 plus b. So yeah, I've got to take my calculator out here, right? 5.45 times 1850 is going to be 10,082.5 plus b. So I've got to subtract that over. And I wind up with negative 10,082.5. That's my b value. So now I know the equation for the use of crude oil in the U.S. because I know my slope and I know my b value. So my equation is going to be y equals, remember, it's your slope, and then plus, which for us is going to be minus because it's a negative, your initial value. Okay. And I'm going to do another one of these. I don't think this is a great example, but I'm going to do another one of these as well. Okay. Now remember, x was the amount of years and y is in billions. So if we wanted to know, like, well, what's happening now in 2021, we could plug that in. I'm going to be lazy and just plug it in. So if I plug in 2021, 5.45 times 2021 minus 10,082.5, you wind up with 931.95 billion crude barrels of oil, or whatever it was, whatever the cubic meters actually of oil. Okay. I'm going to find another example. I just don't like that one. So let me find one in your book. Yeah. Okay, good. I'll do an even one out of the homework for you. Okay. Let's look at, let's look at number 30. It's on page 538, number 30. And again, this is in the section on creating a linear equation using 2 points. So it says you can purchase a motorcycle for $6,500 or lease it for a down payment of $200 and $150 per month. Find a function that describes how the cost of the lease depends on time. How long can you lease the motorcycle before you've paid it off? I don't like that example either, but that's okay. That's not really two coordinates, right? You purchase a motorcycle for $6,500 or lease it for a down payment of $200 and $150 per month. Oh, I see what you're saying. Find a function that describes how the cost of the lease depends on time. Okay, so that's not really two coordinates though. I'm just checking this out real fast, guys. Create the required linear function, and it says 2 data points, but I do not see 2 data points. Well, the cost of the lease depends on time. Yeah, that's not a big deal. Okay, what would the two coordinates be? It gives you the change, right? I mean, a down payment of $200 and $150 per month. So you're decreasing the total or the total you have to pay off by $150 per month because that's your payment, right? But it doesn't give you two coordinates. Okay, well, you know what? This isn't a good two coordinate question. Let's think of what it's saying though. We figure this out. It's not a big deal. So you have a down payment of $200. So that means your initial principal. Now you're going to take $200 off, so it's $6,300, right? So $6,300. Your rate of change is going to be negative $150 per month, right? You're going to make a payment of $150 per month. So the equation would just be your initial amount minus 150x. So this would actually give you the amount you owe on your vehicle, where if y equals the amount owed and x equals the month of the payment, right? So if we look at this, if after 1 month when you make your first payment, take off $150, you're at $6,150, right? So if we looked at after 12 years, let's say after 12 years. So after 12 years, how much do you owe? So not 12 years, 12 months. So you've made 150, or you've made 1,250 payments, right? So the equation would be 6,300 minus 150 times 12. So if we do that, we have 6,300 minus 150 times 12. You would owe 4,500 on your principal still, right? Now I think the question actually asked, how long can you lease the motorcycle before you've paid more than its purchase? Oh, I did not get this example. Oh my gosh, guys. I'm sorry. So I'm seeing what we're saying. I see what we're doing now. Okay. I read this completely wrong. When you read a question and you read it wrong, you got two things going on. You could pay for the motorcycle, it's going to be $650. If you don't have $650 or $6,500, if you don't have $6,500 in your bank account, you can actually put down $200 plus $150 each month for a lease, right? Okay, I see it now. So we're going to make an equation based off the second part, the leased motorcycle, okay? So we'll come back to this, but we're going to look at this lease amount and see how much we've paid on it. So Y is going to be the amount we've paid each month. Or I said amount we paid total, okay? And the X is going to be the number of months. I see this now. So we're going to do Y equals, now initially we paid $200, right? Oh, wait, I'm not going to put units in here. So Y equals 200. So we put 200 plus $150 per month. So like after 1 month, 1 times 150, we've paid a total of $350. After, let's say 12 months for this example. After 12 months, when we plug that in, so it's 200 plus 150 times 12, we've paid $2,000 after 12 months. Now the question though says, how long can you lease the motorcycle before you've paid more than its purchase? So look, how long is it going to take? How long, so our X values, will it take to get to $6,500? So if you look at this equation, we're going to plug the 6,500 into the y because that's the total amount we've paid, equals 200 plus 150x. Now we've got to solve for this x. So I'm going to subtract the 200. So I get 6,300 equals 150x. Then I'm going to divide by 150. And I wind up with x equals, now 6,300 divided by 150, 42. So it turns out after 42 months, you could have just paid for the vehicle, okay? You could have just paid for the vehicle. In the 43rd month, you're paying more than the value. And really, at that point, the vehicle isn't worth $6,500, right? That motorcycle, that's like it's 3.5 years later, right? It's not worth $6,500. You've driven it for 3.5 years. It's worth a lot less than that. Okay, gosh, I got that kind of mixed up. Okay, so for homework though, I do want you to do 1 through 53 odd. This is in 9B, and it starts on page 536. Oh gosh. Where did I write that? Right there. 9B, page 536, 1 through 53 odd. Okay, I'm going to stop the live stream.